Hello everyone, I am Zishan Akhtar and I will give a small presentation on our work titled Momentum-Based Projection-Free Stochastic Optimization under Affine Constraint. This is the main problem which we intend to solve. We have a stochastic objective function with affine constraint, but we have additional constraint over the set calligraphic C, which is costly to project on. Let us consider the problem of max cut in a graph. It is well known that such problems can be formulated using SDP relaxation, which results in affine constraints. Now suppose we have additional trace constraint. Use of projection-based algorithm for solving such problems can be computationally very expensive. So we target to develop projection-free algorithm for stochastic optimization problems with affine constraint. How existing methods like proximal methods that need to perform projection at each step deal with such problem? The answer comes in the form of Frank-Wolf methods, which solves a linear minimization problem instead of solving the quadratic projection step. So what is stopping us from directly using Frank-Wolf in our main problem? This is mainly due to the affine constraint. Actually, we can rewrite our problem to incorporate a affine constraint into objective using an indicator function as shown in equation 2. But this makes the overall objective function non-smooth, and it is well known that Frank-Wolf analysis require objective to be smooth. To our rescue, Nesterov smoothing comes into play, which is shown in equation 4. So we start with smoothing our indicator function and rewrite our problem using this smooth version. Now we are free to use Frank-Wolf methods. In literature, there are projection-free algorithms to deal with such problems. For instance, a CGM proposed in 2018 shows optimal guarantee of order k to the power minus 1 by 2, which was extended for a stochastic objective in 2019, but that settled with a convergence rate of k to the power minus 1 by 3 in objective. So the possibility of improving the convergence rate for stochastic cases remain open, and this is what we have actually explored in this work. The existing method use gradient tracking technique is shown in equation 6, which resulted in suboptimal performance. We overcome this suboptimality by employing a 2-point estimate of gradient given in equation 7, which is proved to be a better way of tracking gradients. Once we track gradient, we obtain the gradient of smooth indicator function for affine constraint, solve the usual linear minimization problem of Frank-Wolf, and then update the primal variable as given in equation 10. Such approach help us obtaining optimal convergence rate of order k to the power minus 1 by 2 in terms of both objective and constraint violation as shown in equation 11 to 13. We verify our theoretical contribution on the clustering problem, which is shown in equation 14. Basically, the constraint calligraphic C has additional trace constraint, which is expensive to project on, and hence the proposed method is best suited to solve such problems. The comparison graph justifies our claim. We can see that proposed method is performing as good as deterministic algorithm, beating the state-of-the-art method. That's all. Thank you.